Hi everyone, so today we are here with the new problem, and the problem name is unique path 2, and this is a medium type of problem, and it is between easy and medium actually if you solve the yesterday problem, then it is very easy for you to solve this problem also. Okay. Yesterday, due to some reason, I am not able to shoot that video, but yes, today I am available. So yes, let's come to this problem. What is the problem, and then see how we can solve it. So basically, in this problem, we have m cross n matrix. As you can see in here, we have m cross n matrix, and in that, at zero row, zero column, at top right column, there is a robot, right? And this robot have to go to this bottom right corner, okay, which is the last cell of this matrix. And within this matrix we have obstacles too. As you can see, this is an obstacle, right? So we want to find the number of ways this robot can reach to the last cell of this matrix, and we have to find how many ways are there, right? And wherever we have a obstacle, we are not able to go through that path. So that is the whole problem, right? And we have to given we have to tell how much ways we have. Now if you see this, you can see the first way the robot can go from there and reach to this. So this is one way. The another way is robot can go down first and then right. And one more thing here, we only have two things. Like this robot can move only in two direction. The first one is down direction, and then second one is the right direction. So these are the two direction robot can move. Okay. And we have to do these movements and find out the number of paths we have such that this robot can reach to the last index. Now if you know the DFS BFS, how we can solve it, it is very easy. Obviously, let's suppose we have an array, right? Sorry, we have a matrix, right? And let me create one. And one more thing, the 0 tells the path is clear, the 1 tells there is an obstacle. So it is like that. So if I write 1 here, 1 here, 1 here, not here. So other than that, we have 0, 0, 0, 0, right? Let me write zeros, lot of zeros over here, right? And let's add more 1, so that it is easy for us. uh, that's fine, I think. Yes. So now you can see what we do. We can simply we are here, right? We are here, so we can simply call recursion to the right side and ask recursion how many ways we have if we start from right side. So the recursion gives us the total number of ways, right? And similarly, we are here and we are calling recursion to the downside, right? And we ask how many ways we have such that we can reach to the last cell. So recursion gives us the total number of ways if we start from down, and whatever the ways we are getting from right and whatever the ways we are getting from down, we simply can add it. Okay. And that is the total number of ways we have. Okay. So just a minute. Yes. So in that way, when we reach at this point, recursion call down and recursion call bottom. Sorry, down and right. This is down, this is right. So whenever at any point we find one, we are not able to go through that cell. So we are not able to go through that cell. So we can simply go through this. When we reach a recursion call this side and this side, but we are not able to go here. Now when we are here, recursion call right and down. Here it is out of boundary, so we have to check whether the call is out of boundary. If the call is out of boundary, we have to return from this read 0. And now we are here, we have to call right, but it is out of boundary, so we call down. It is out of boundary, we call down. Now when we reached at last cell, we can simply return 1 and we can store 1 here, right? Because this is the point when it calls bottom and it says there are one way to move from this cell to this cell, so there is one way. Similarly this returns one, similarly this return one, so we actually return one 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 one. So this, there is a one way if we move like this, so there is a one way. Let me change the color once. So there is a one way. Similarly we can go here, then recursion call there, then recursion call down, and then recursion call down, but it is out of boundary, so we return. Then recursion call right, it calls down, but it is a boundary, so it calls right, it calls right. In that way there is one more way. So in totality we can simply add the total number of ways, and we have two, right? And that is how we can easily solve it. So what are the things we have to consider? The first is, if cell is equal to 1, we, this is an obstacle, in that case we can simply return the 0. The another thing is, if the calling cell where recursion call, if it is out of boundary, right, if it is boundary case, right, we can say if it is a boundary case, in that case we can also return 0. The third point is, what we can do, the third point is, when we reach at m minus 1, sorry, n minus 1 cell, means the last cell, in that case we have to return the 1, right? But in that case what is actually happening, there are total m cross n cells, right? And for each cell we have to call recursion. So it actually have a lot of it takes a lot of time if we do like this. It total takes m cross n, which is, as you can say, n square in totality, right? So which is a very high time complexity. So in order to solve it, in order to optimize it, what we do, we are basically using the concept of dynamic programming. What we do in the dynamic programming, we basically find some sub problems, right? And the solution of those sub problems we save somewhere in some data structure, and whenever we need whenever we need the solution of that sub problem, we can simply use it. What it means, let's understand once how DP works. So if I take, let's suppose, this matrix, right? Let me create one matrix. Okay, let me create one matrix. Okay, now let's suppose let me add let's suppose everyone is 1, and like everything is 0, and these are ones, right? So let's suppose whenever we come from there, this side, and then this side, then this side, right, then this side, then this side, and this side. So this is one path, like this is one path, right? And when we go from there, here we move down, but if we move right, and then if we move down, so the total number of path this cell have, let's suppose if like this cell, if we move from this cell to this cell, how many paths are there? There are total one path. From this cell to this cell there are total one path, right? So when from this we move there, and when we move down, we find that there is a one way such that we can reach at the end point of the cell. We can simply check if there are one way, we can simply use this solution and add into it. So if there is one solution, so we can simply return one from there, because if we move from there to there, there is only one solution we have, right? Let me give one more example. So if I go like this and go like this, so when you reach here, so you know from there to there how much let me change let me take a highlighter. So from there to there, how many paths are there? Only one. So we don't have to iterate all this cell. We can simply store that at this point, that there is one way, there is one way to reach at last cell, and we can simply use it and return from there. In that case, A lot of iteration, a lot of recursion calls we can save, and we can improve our time complexity. But let's see how we can basically doing it. So it is a very basic DP problem. What we do, we basically create a DP matrix, and DP matrix is nothing. The matrix we have similar a dummy matrix we create to store the sub problem solutions, and we are at the 0th first index of the matrix, and here we are checking whether we reach at last cell or not, and here we checking the boundary condition. If at last cell there is 0, it means that we are able to reach at last cell, we have to return 1. But let's suppose if at the last cell we have 1, so 1 means obstacle, and in that case we are not able to reach at last cell, and we have to return 0. In the boundary case, or if there is an obstacle, we have to return 0. And what we do here, we basically call bottom, so down and right recursion. And for ij cell, if there is a solution, initially every dp matrix is filled with -1, right? And let's suppose we are finding a solution for some cell, and if it is equal to -1, it means its solution is not concluded yet. So we basically call recursion, and whatever the total number of paths we get from down and right side, we basically add it and save it in that cell and return it. And let's suppose uh, in future the this cell is again called, so we can check whether for this cell, if answer is there, we can simply return it, we don't have to compute it again, right? And that's how we basically save a lot of time. I hope you get it, how we basically use recursion here, and if you like it, please share and subscribe. Thank you.